तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
The next topic we will take up for discussion is network theorems. I am sure that you have had acquaintance with the various types of network theorems in your earlier circuit analysis courses, like the superposition theorem, Theorems theorem, Norton theorem, and so on. So we will have a brief review of the various network theorems, and this will be, as I said, a review of what you already know, but perhaps it will deepen your understanding of the theorems in one or more respects in respect of certain theorems. You may also learn a few additional theorems which you have not been exposed to in your earlier courses. But the novel feature of what we are going to discuss here from your point of view may be the application of these theorems in the Laplace transform domain, which is of course a new feature which you would not have had in your earlier courses. Now, network theorems furnish a particularly simple solutions of network problems in special cases. So oftentimes the solution of a particular problem using the routine methods may entail long computation or calculations, but if you use a particular theorem which is relevant to the problem on hand, then the solution may become quite simple and straightforward. So after studying the various network theorems, one should develop the facility of identifying a particular theorem which fetches us the solution in the most direct and simple way from the whole lot of theorems that are available to you. So this discrimination and the facility of choosing a particular theorem relevant to the context is something very important. Secondly, network theorems also provide us special insights into the network behavior quite often, and this is an additional reason why we study network theorems. As you are aware by now, there are three main realms of network analysis using the algebraic method. One is the DC circuit analysis methods, then the AC circuit analysis methods, then the methods using the transform diagram in the Laplace transform domain. All these three methods have a common set of techniques of network analysis. Whether you use the loop current method or the node voltage method, the principle, the essential basics of the network analysis methods are the same. However, in the case of DC circuits, you write the equations in terms of various constants, which are the resistance of the network or the conductance of the network, and the variables which are DC quantities which are constants. In the case of AC circuit analysis, the constants are complex constants and the variables are the phasors of the voltage and currents which you are trying to solve. In the case of Laplace transform technique, the equations once again turn out to be algebraic, but the coefficients of the various variables that you are trying to solve for are functions of S, algebraic functions of S. The impedance functions, the admittance functions are functions thereof. And the variables themselves which you are trying to solve for are functions of the complex variable S, the transform of a voltage, the transform of a current, as the case may be. So all these in all the three domains, whether it is the DC circuit analysis, the AC circuit analysis, or the transform domain, essential techniques are one and the same. However, the details will vary, and so provided you pay special attention to the small details which are demanded by the requirements of the particular realm, you can be assured that the general principles governing the network analysis are the same. Consequently, the network theorems that we are going to talk about also have validity in all the three domains, whether the DC circuit analysis, AC circuit analysis, or the transform domain. So what we will do is try to give the statements of the various network theorems and try to discuss them in the most general context, which is the Laplace transform domain, and its simplification when it is the AC circuit analysis or the DC circuit analysis will be almost evident. So let us now start with a review of the superposition theorem, which I am sure all of you are familiar with already in the context of DC circuits or AC circuits. The statement of the superposition theorem would be something like this. In a linear network, acted upon by several sources, I would say, let us say, several independent sources. The response in any element of the network, of course, is the sum of the responses obtained with one source acting at a time. The other sources being deactivated. The other sources being deactivated. Since I am sure you already know about this, we will not elaborate on this, except of course to point out that when you have a whole lot of sources acting upon a linear network, the crucial statement here is a linear network. In a linear network acted upon by several independent sources, then if you want to calculate the response in any particular quantity, in a particular element, say the voltage response or current response in a particular element, it is obtained by the superposition of the responses obtained by the individual sources, each one acting at one time, and when the particular source is acting, all the other sources are deactivated. So we specifically mention what is meant by deactivation in a moment. So comments on this. Is the superposition, when we talk about superposition, it may be you have several sources distributed in the network, so then you take one source at a time. It can be superposition of several sources distributed in a network. So each source you take at a time. Alternately, if there is a single source, you can decompose that. You can resolve that into several elementary sources, much as we have done in the case of Fourier analysis, and consider the effect of each source at a time, or superposition of the elementary sources into which a single source is resolved. So in other words, it may be the spatial distribution of the sources which you are superposing, or a single source at a given location which is resolved into the sum as a sum of several elementary sources, and then you find the effect of each source in turn. So that means a temporal, or if it is a waveform, it may be a particular source may be resolved into several functions of time, independent functions of time, like a Fourier analysis, the resolution of a periodic waveform into several sinusoids, or it could be a spatial type of distribution in which you take the effect of one source at a time. Second comment is deactivation means voltage sources are replaced by short circuits, because the voltage strength is made equal to 0. That means a particular voltage source is replaced by short circuit. Current sources, if there are any, and when you are considering the effect of other sources, a particular current source is replaced by an open circuit. Current sources are replaced by open circuits. In other words, you are reducing the strength of that source, whether it's a voltage source or current source, to 0. So when you are reducing the strength of a voltage source to 0, it means you are replacing it by a short circuit. If you are replacing the strength of a current source, if you are reducing the strength of a current source to 0, it means it is replaced by an open circuit. Third point is, when you are considering the effect of these various sources at a time, it is only the independent sources that you should consider. Dependent sources, if there are any, they form part of the linear network. A linear network contains linear elements, and the linear elements include the dependent sources also, because the dependent voltage source is linearly dependent on the controlling source, controlling quantity. Therefore, dependent sources must be left intact. Dependent or controlled sources must be left intact. That means you should not disturb them when the independent sources are deactivated. So that is important. So if you have dependent sources, those dependent sources must be allowed free play as far as computation of the effect of one particular independent source is concerned. Dependent sources should not be disturbed, they should be there. Of course, their value depends upon the particular situation in the circuit. The fourth point which we should like to observe is, when dealing with differential equations, differential equation approach, the superposition principle applies to A. Suppose you are taking up the differential equation approach to the solution of a network problem, and then you have several sources and you consider one source at a time, then you would like to find out the response due to each source in turn. Then you can superpose the responses to the individual sources, provided the response that you are talking about is a particular integral solution. So superposition will be applicable to particular integral solutions. Alternately, the total solution with zero initial conditions. So you can superpose the responses if they are in the form of particular integral solutions, or alternately, if the total solution is what you are looking for and you want to superpose this total solution due to each individual source acting at a time, then the superposition principle is valid provided the network has zero initial conditions. This is because when you have an initial current in an inductor or an initial charge on a capacitor, it spoils the linearity of the terminal relations of the equations, terminal relations between the voltage and current in an inductor or a capacitor. You may recall that all such non-zero initial conditions associated with inductors or capacitors can be replaced by equivalent independent sources, either DC sources or impulse sources, and the Laplace transform domain analysis incorporates such equivalent sources to replace the initial conditions. Therefore, it turns out that in the Laplace transform domain, if you replace each initial condition by an equivalent source, then we are essentially dealing with a network with zero initial conditions acted upon by several independent sources, including those sources which have replaced the non-zero initial conditions. Therefore, such a problem does not arise. That means in a Laplace transform domain, when you have several sources, including the replacement sources for non-zero initial conditions, you can take the effect of each individual source at a time and superpose those effects. In fact, the statement here, a linear network, emphasizes that we are talking about a network with zero initial conditions. Additional points: we can also observe that when you are superposing the responses, you must understand that the superposition principle will not be valid for superposition of powers. Powers cannot be superposed. In general, when you want to calculate the power in a particular element, you can't calculate the power due to each individual source at a time and add up the powers and say this is the total power when all the sources are acting up at a time, because power is non-linearly related to a voltage or current, as the case may be. However, there are special exceptions to this, because in such cases the power can be superposed. Exceptions are: one, when sources of different frequencies, when sinusoidal sources of different frequencies are acting, in which case, because as you have seen when we talked about in Fourier, we talked in terms of the calculation of power when we are discussing the Fourier series, that the cross product of two different frequency terms, they will have a zero average. Therefore, it turns out when sinusoidal sources of different frequencies are acting, can calculate the power due to each source at a time, each frequency source, and then superpose them. The total power can be superposed in this context. Secondly, it may arise that when two sinusoidal sources of the same frequency but with 90 degrees phase shift are acting. So if I have one sinusoid which is sin omega t type of thing and the other is cos omega t, you can find out the power due to each individual source and add them up, because it turns out that the magnitude of a plus jb is square root of a squared plus b squared. Therefore, if you from that relation you will find that when two sinusoidal sources of same frequency but with 90 degrees phase shift act, then also power can be superposed. A third interesting situation arises when a DC network, that is a resistive network, is acted upon by voltage and current sources, then the total power dissipated in the network total power delivered by the sources is the sum of powers delivered by voltage sources alone and powers delivered by the sum of powers delivered by the voltage sources alone and power delivered by the current sources alone. This is a very special result which is interesting, that if you have several voltage sources and current sources acting upon a resistive network, then you calculate the total power delivered by the voltage sources acting alone, all the current sources are open circuited, then let us call that PV, then find out the total power delivered by the current sources acting with the voltage sources deactivated, let us call that PI, then the total power is PV plus PI, which is the superposition of these two powers. These are exceptional cases, special cases. Then lastly, we might like to ask at this point, what is the advantage of the superposition theorem, application of the superposition theorem to network analysis? One answer to this is that if you have a complicated network acted upon by several sources, then the network analysis method that you have to apply may be a general one, like the loop current method or the node voltage method, which requires a considerable algebra. On the other hand, if you are taking only one source at a time, it may be that the whole network configuration may be one of the series parallel type. Therefore, the analysis technique that you would employ would be one where you combine two elements in series or in parallel, and the analysis may be that much simpler. So this will not be possible if you have two or three sources present at the same time. Therefore, by using the superposition theorem, you may reduce the complexity of the network or the configuration of the network to a simpler form, and the analysis may be that much faster. So by taking the effect, taking one source at a time, series parallel reduction technique may be possible, which is precluded when all the sources are acting together. Secondly, superposition theorem provides certain insights in the network behavior. When you apply that superposition theorem, you may be able to find out certain characteristics of the network behavior using the superposition principle, and also you may use this for proving other results. For example, you have already seen that using superposition we can see that the response of a linear system to a composite signal can be thought of as the superposition of the responses due to an impulse functions or step functions, and you have got superposition integral or the so-called fault-tuning integral or convolution integral. So superposition principle can be employed to derive some other results and to get additional insights into the behavior of the system. So with this introduction about the superposition theorem, which as I said is a quick review of certain points which you already know and maybe refining some concepts which you have earlier been exposed to, let me work out a couple of examples. Okay. Let us now consider an example where a voltage source Vs, which is 4 plus cos t, is acting upon a series RC circuit, and it is given that Vc0 is equal to 2 volts. Now if you set up you are interested in finding out Vc of t, so if you want to find out the differential equation joining Vc as the output quantity with respect to Vs as the input quantity, we see that Vc plus the voltage drop across the resistance must be equal to Vs. The current in the capacitor is C dVc dt. Therefore, the voltage across the resistance is R times C dVc dt. Therefore, you have RC dVc dt, that is the voltage across the resistance, plus the voltage across the capacitor must be equal to Vs. And this can be written as dVc by dt plus 1 over RC Vc equals Vs by RC. So the solution for this can be obtained in the usual manner. The particular integral solution for this would be, of course, 1 over d plus 1 over RC operating on Vs upon RC, and using the forcing function that we know, we can find out the particular integral solution, and using the initial conditions, finally you can arrive at the solution, total solution for Vc as 4 minus 2.5 e power minus t plus half of cosine t plus sine t. That will be the total solution for Vc of t. Now let us use the principle of superposition and try to find out the solution in the classical differential equation approach itself. So let us take Vs to be equal to 4 volts, a DC source at once, and then let's take Vs is equal to cos t a second time and superpose the effects. So if I take Vs as 4 volts, so you have a 4 volt source and then you have a resistance and a capacitance Vc. So the particular integral solution for that, when you have 4 volts DC, Vc will also be equal to 4 volts. The complementary function for this Vc will turn out to be minus 2e to the power of minus t. Therefore, the total solution taking Vc0 to be 2 volts. So if you take the total solution, this is particular complementary function is also taken with that initial condition. This will turn out to be 4 minus 2e to the power of minus t volts. That is the Vc. Now on the other hand, you take the source to be a sinusoidal function cos t, and then you have RC network, and if we have 1 ohm resistance and a 1 farad capacitor. So you find out the impedance of this. This is cos t, omega equals 1. Impedance is 1 minus j, that is root 2 at an angle of minus 45 degrees. So if cos t is the driving voltage and the impedance is root 2 at an angle of minus 45 degrees, it turns out that the particular integral solution is 0.5 cos t plus sin t. That is the particular integral solution. And complementary function will turn out to be 1.5 e to the power of minus t. Therefore, the total solution is 1.5 e to the power of minus t plus 0.5 cos t plus sin t. Now, if you add these, the total particular integral solution is 4 plus 0.5 cos t plus sin t. If you take the sum of the total solution, this is 4 minus 2 e to the power of minus t minus 2 e to the power of minus t plus 1.5 minus et. Therefore, 4 minus 0.5 e to the power of minus t plus 0.5 cos t plus sin t. This is what you get. Now, if you compare these two expressions with the result that you would obtain under normal calculations, you will observe that 4 plus half cos t sin t, the particular integral solution here, is the correct one. However, in the total solution you get 4 minus 2.5 e to the power of minus t plus this, whereas here you get 4 minus 0.5 e to the power of minus t. The discrepancy arose because when you are calculating this total solution, you have taken the initial capacitor voltage to be 2 volts. When you have taken this, with the second source, you have taken the initial capacitor voltage once again as 2 volts. Therefore, when you are adding this up, you are getting the initial capacitor voltage as 4 volts, and that's what this gives when t equals 0. So the total solutions will not add up because you have taken the initial capacitor voltage as 2 volts. On the other hand, if you have taken the total solution taking the initial capacitor voltage to be 0 volts, you would get some value, and if you replace the initial voltage across the capacitor by an additional DC source of 2 volts, then you get the total solution correctly. So you can work that out. I will leave the details to you. Then you take 3 sources now. You replace the initial capacitor voltage by a 2 volt source. That means you take a 4 volts DC source here as before, then a cos t term, a resistance here R equals 1 ohm, and the capacitor you replace it by an uncharged capacitor plus a 2 volt source representing the initial conditions, and you take this to be your VC and calculate this VC using this source at one time, this source as one time, and this source as another time. You will get the correct solution even if you superpose the total solution. So that is what we meant earlier, that you can superpose the total solutions with 0 initial conditions, because now this capacitor is assumed to have 0 voltage, because whatever non-zero initial condition was there, it is replaced by an equivalent source. Let us take another example. Let us consider a second example in which you have an independent voltage source, independent current source, and a dependent voltage source. So we would like to use the superposition principle to analyze this network. So we consider this voltage source acting, therefore 4 volts, and you have 1 ohm resistance, another 1 ohm resistance, and you have a dependent source. Dependent source, as I said, should be kept intact. You should not disturb that. So if this is Vi, this is 4 times Vi, and you have 1 ohm resistance and another 1 ohm resistance, and this current source is open circuit. So in this network, you have 4 volts driving a 2 ohm resistor in this circuit, therefore a current of 2 amperes flows through that, and consequently, I am sorry, this is 1 volt. I have 1 volt here, therefore this should be 1 volt. Sorry, this is 1 volt, and consequently the current here is half an ampere, and Vi is 0.5 volts, and 4 Vi therefore is 2 volts. And this 2 volts will drive a current of 1 ampere through this, and you will develop a voltage of plus 1 volt across these two terminals. And that is the complete analysis of this circuit with one voltage source only acting. Now we also have a current source, therefore let us find out the performance of this circuit when this 1 ampere current source only is acting and this 1 volt source is replaced by short circuit. So you have circuit like this is Vi, and once again we have the dependent source 4 times Vi, and you have 1 ohm resistance, another 1 ohm resistance, and you have a current source of 1 ampere. Now let us see what happens. As far as this loop of 2 resistors are concerned, there is no driving voltage here, therefore the current here is 0, and the voltage Vi also is 0. If this voltage Vi is 0, this is also 4 Vi is also 0, which means that this 1 ampere current source is acting on 2 1 ohm resistances in parallel, which means the current here must be half ampere and the current here must be half ampere. So that completes the analysis of the circuit with 1 ampere source acting alone. Now you can put these two results to find out what happens in the original circuit. So you can see in the original circuit the current in this loop is half ampere here, 0 amperes here, therefore in the original circuit also the current is half an ampere. The voltage Vi, let me put this in different color so that we understand the result that we have obtained. So this is half ampere. The voltage Vi is the voltage here plus the voltage here. The voltage here is 0, the voltage here is half volt, therefore this is half volt. 4 Vi, this is 2 volts here, this is 0. This is of course 0 because Vi is 0, this is also 0, therefore this will be 2 volts. The current across the current source, this current source drives a current of half ampere here, half ampere, therefore the voltage across the current source is half volt here. This is half volt, this is 1 volt, so the voltage here is 1.5 volts. Across the source. And the current here, this is 1 ampere in this direction, half an ampere in the other direction, therefore this is 0.5 ampere, half ampere here. The current in this element is 1 ampere here, half an ampere here, therefore this is 1.5 amperes. And this must be, because 1 ampere in this direction, half an ampere in the other direction, this current must be half an ampere in this direction. So this half ampere and this 1 ampere together will go as 1.5 amperes in this 1 ohm resistance. So now this particular example illustrates the application of the superposition theorem when there are dependent sources also are present. As I pointed out, the dependent sources must be kept intact when you are considering the application of each independent source at a time. The next theorem that we will discuss is what is called the substitution theorem. It reads like this: if an element in a network is replaced by a voltage source whose voltage at every instant of time equals the voltage existing across the element in the original network, then the conditions in the rest of the network are not altered. Let me illustrate this first by means of a simple example, and then later on I will discuss this. Suppose I have a 2 volts source acting on a circuit like this. Then the voltage across this 1 ohm resistance is obviously 1 volt. So suppose I replace this by a 1 volt source and consider this network 2 volts 1 ohm, then the current in the network, everything else will remain the same. Here we have a 1 ohm 1 ampere current, here also you have 1 ampere current, the voltage across this resistance here and here are the same. That means this element which had a 1 volts potential drop across this is replaced by a source. So that is the statement of this theorem. In general, you have a network here, and let us say that we have an element here, maybe linear, maybe non-linear. That element we have not made any particular stipulation. It has, in the Laplace transform domain, let us say it has a voltage Vs, and it has a certain current Ifs. Now what this substitution theorem tells us is that in this network, if you replace this element by a voltage source whose voltage is Vs, which is the same as this, then all the other conditions in the network will remain the same. Suppose I have an element here whose voltage is Vk and whose current is Ik. In this will continue to be Vk and the current will be Ik. What is the justification for this? Justification is that if you are doing the node voltage method of analysis, let us take this as the datum node, take this as the datum node, then the node equations at all other nodes inside the network will remain the same. As far as this node is concerned, in the original network, V of s is a solution for this node voltage. Now here we are stipulating that node voltage to be Vs. So this node voltage stipulation is consistent with the solution that is obtained in the original network. The other node equations are the same. For this particular node, you are giving the solution itself as the data, therefore it is consistent. Therefore whatever solution you obtain here will be the same as this as far as the other nodes are concerned. Similarly, if you are using the loop equations, the other loop equations are the same. In this loop equation corresponding to Ifs, across this particular element you have some, for example, Zs times Ifs, something would have written, and now whatever solution you had obtained for this is now incorporated here. So the stipulation for this loop equation is consistent with the solution. The other loop equations are the same, therefore the solution for the other element responses will be the same. This is the principle of the substitution theorem. Now there are a couple of points which I would like to emphasize here. We don't have a tremendous advantage in using the substitution theorem to solve network problems. However, it turns out to be very useful in proving some other theorems. Using the substitution principle, we can use several other theorems. Also, in some cases where the switches are opened and closed, you can apply the substitution theorem and get special insights in the circuit behavior and also the total solution in a fairly straightforward fashion. So that is the usefulness of the substitution theorem. Second point I would like to emphasize is that the element that you are replacing can be linear or non-linear, doesn't matter what it is. A third point is, when you replace, for example, when you, in this particular case, let us take the same case here. Suppose I have a similar case, not the same case. Suppose I have a case here, you have a 2 volt source acting upon a 1 ohm resistance. So the voltage across this is 2 volts. Now suppose you replace this 1 ohm resistor by another 2 volt source. So we have this resultant circuit. And what is the current in this? It can be anybody's guess, because this is a particular type of circuit in which any current I is a possible solution. So this network, we can say, is not solvable, because you can't have a definite solution for this network. So we have used the substitution theorem. This is one particular solution which is equal to 2 amperes is also a solution, but that is not a definite solution for this network. So when you use the substitution theorem, we must also have a proviso that the altered network must be solvable. Otherwise, you get an indefiniteness. You may end up with a situation where multiple solutions are possible, there is no definite solution, and such circuits are said to be not solvable. So when you use the substitution theorem, you must ensure that the altered network is solvable. As an extension of the substitution theorem, you can also say when a current is flowing through a particular element, you can replace this by an equivalent current source. So you can also have a current source IFS. This is an alternative form of substitution theorem. You can replace this particular element by a current source whose value at every instant of time is the current in the original network. So you can replace this element by a voltage source or a current source. This is also a substitution theorem, which is an alternate version of the main theorem in which we said an element can be replaced by a voltage source. As I mentioned, the substitution theorem gives us some special insights into circuit behavior particularly when switches are opened and closed, which we will see later, and it is also used to prove several other theorems. This is the special advantage of the substitution theorem. So in this lecture, we have started the discussion of various network theorems. As I mentioned, network theorems are used to simplify the analysis of networks in particular cases, and depending upon the problem on hand, one of the network theorems may be quite appropriate to apply. It provides us a solution in a straightforward fashion. So we should develop the ability to choose the particular theorem which facilitates the solution in the most effective way in a given situation. And we talked about superposition theorem, in which we said the response of a particular element situated in a linear network, when it is acted upon by several independent sources, can be obtained by finding out the response in that element with each source acting in turn, keeping all the other sources deactivated, and superposing the individual responses to get the total response. We mentioned that in the case of deactivation, what we meant by deactivation is that the voltage source strength is reduced to 0 and the current source strength is reduced to 0, which means that the voltage is replaced by a short circuit, the current is replaced by an open circuit. And this is to be done for all independent sources. Dependent sources, if there are any, must be kept intact. They are part of the linear system. Secondly, we observed that when you want to find out the transient solution in a network, then the superposition principle can be applied with 0 initial conditions in the system, or with all initial conditions replaced by equivalent sources, and therefore the principle of superposition can be extended to the sources which stand for the non-zero initial conditions. And this is what we do in the Laplace transform domain, where non-zero initial conditions are replaced by equivalent sources. We also mentioned that the superposition principle can prove to be effective when we take one source at a time. The network configuration becomes simpler, like in the series parallel structure. Then we can use the analysis with each source in turn by taking recourse to the simplified form of network analysis provided by the series parallel structure. Whereas if we had more than one source, such a series parallel reduction technique may not be possible. We observed that power cannot be superposed in general, but there are a few exceptions which we pointed out. Then we discussed the so-called substitution theorem, where in a given network, if you so choose, a particular element can be replaced by a current source or a voltage source, the current source being having a value which is equal at every instant of time to the actual current that was existing in the network, original network, and similarly the voltage source. Then the question that you will naturally ask is, if you know the current in the network, then what is the purpose of using the network theorem to solve for it? The answer to that is, we don't use the substitution theorem to find out the current in a network in most of the cases. We use this as a kind of artifice or a tactic to prove other network theorems. Also in some cases it turns out that where you are opening or closing the switches, replacement of an open switch or a closed switch by a suitable current source or voltage source, as we will see, will be effective in providing us a solution which is a straightforward one. We will discuss other network theorems in the next lecture, but before that let me mention that a third network theorem, which is called the Reciprocity Theorem, is something which we had already discussed. I can just reiterate now that if in a linear reciprocal network which consists of bilateral elements and reciprocal elements, the ratio of the Laplace transform, the response involvement, response to the excitation Laplace transform, is the same when the locations of the response and excitation are interchanged. This is true in a network containing bilateral elements and reciprocal elements. This is something which we already discussed when we are discussing the two-port network characteristics. So we will not discuss reciprocity theorem specially here as one of the network theorems. This we will assume has already been discussed with this. But however, some ramifications of reciprocity theorem will be discussed when we talk about Telegraph theorem at a later point of time.